Hello, everybody. Thanks for attending this third lecture, the last of the series. I'll be speaking about polynomial optimal control today. As before, I will give a certain number of exercises. I gave exercises last week during the second lecture, and I may get back to these exercises if you want me to do so at the end via the chat. As to the exercises of the third lecture, I will post in due time a written solution to all of them for you to check out. So let's start the lecture of today. Which will be about polynomial optimal control. So again, I recall the main steps of the moment sum of squares, as known as LAAS hierarchy, to solving nonlinear non-convex problems. First, we'll reformulate this nonlinear problem as a linear problem at the price of enlarging or changing the space of solutions. The second step will consist of solving approximately the linear problem, which is generally infinite dimensional, with the family or hierarchy of tractable convex relaxations of increasing size. Typically, the convex relaxations will be relying on our linear programming, quadratic programming, or more generally, semi-definite programming. The third step is about ensuring convergence of this numerical scheme. So either we got a certificate that the original problem is solved at the price of solving a convex optimization problem of finite size. This occurs, for example, in polynomial optimization that was covered during the first lecture, or its solution is approximated with a quality that increases when the size of the convex relaxation increases. This was the case of the last week lecture on maximum positively invariant set approximation, and this will be the case today as well for polynomial optimal control. And at each step of this three-step procedure, the use of conic convex duality proves to be very important. So today I'll go through polynomial optimization and I will follow the same pattern as usual. So what is polynomial optimal control? POC for short. We can view it as a time-varying extension of a POP, of a polynomial optimization problem. So here, the quantities of interest are the control signal, which is denoted by U, and the state signal, which is denoted by X. Both are functions of time, denoted by small t, and they are linked through ordinary differential equation, whereas the dot here above the X symbol means the time derivative. So X dot means dx over dt, the velocity of the state is enforced to be equal to a function of the state and the control. This function is denoted by f. So the state vector typically lives in Rn for n equals to 1, 2, 3. And U, the control, lives in vector space Rm for m generally smaller than n. The ordinary differential equation is starting at time t0 in blue here. And at time 0, we prescribe the value of the state to some given value x0. On the top of that, we have constraints on the state. So the state for all time belonging to t0, capital T being the terminal time, must belong to a given constraint set, capital X. Similarly, the control signal for all time must belong to capital U, control set. The terminal time, the value of the state at terminal time, X capital T, also is constrained to a given subset of capital X, denoted capital X, capital T. So in general, with these constraints, there are plenty of solutions to the, let me erase that. There are plenty of solutions to the ordinary differential equation because of the freedom in the choice of controls. And we may be interested in finding a trajectory such that some performance criterion or cost is minimized. So this is this integral cost here, integral of some function, scalar valued, L, function of the state and of the control, integrated with respect to time uniformly, plus some terminal cost, L sub capital T, evaluated only at the terminal state. So the initial data is in blue here, it's T0, X0, and the value of the cost, the best possible value of the cost that can be achieved, is denoted by V star, and it's a function of the initial data. This function V star is called the value function. The name polynomial here refers to the fact that all the data are algebraic or semi-algebraic, namely the dynamics, the velocity here prescribed, F is a polynomial map. The integrand here is also called the Lagrangian. L is a polynomial of X and U, and so is the terminal cost, L sub capital T. The sets, capital X, capital U, capital X, capital T, are semi-algebraic, namely there will be compact basic semi-algebraic sets, so intersections of finitely many polynomial superlevel sets. The terminal time capital T can be either given, fixed, or free. So this is a setup that will keep us busy today: polynomial optimal control, a generalization of polynomial optimization to time-varying data. So in contrast with the lecture of the previous week, here you see that we do not have a discrete iteration, we have a continuous variation. The velocity at each given time is prescribed. This is an ordinary differential equation, not a difference equation. So I insist already here on this quantity, the value function V star, because it turns out to be very important in optimal control. The reason is that from the value function, actually, we can solve the optimal control problem. We can derive an optimal control just by solving an optimization problem. Right? And I said just by solving, this is not a trivial task. This is a time-varying optimization problem. But basically, from the derivative respect to x of the value function V star, we can derive an optimal control law for each given trajectory. So at each given time, we measure the state, we assume V star is given, then we can deduce the value of the optimal control policy. We can also, thanks to the value function, verify optimality of a given trajectory and given control law via this equation here. And if you're familiar with optimal control theory, you may have recognized that this structure becomes something which is rather easy to solve using numerical linear algebra. It is called the Riccati equation. So actually, in general, for nonlinear dependence of the dynamics in the control and the Lagrangian in the control, this can be a challenge to solve for the value function, to find the value function V star. Actually, one has to solve a nonlinear PDE called the Hamilton-Jacobi-Bellman equation. It's a first order nonlinear partial differential equation, which looks like that, where here H denotes the Legendre conjugate to the Lagrangian. It's called the Hamiltonian. It's defined like that. And it turns out that in general, this equation does not have a regular solution. So even the notion of gradient here is not well defined. Typically, it's not differentiable. So one has to give a meaning to this notation. And this is the notion of viscosity solution, a notion of weak solution that must be defined. So it is not the purpose of this lecture, but I just want to illustrate the potential difficulties and the lack of regularity of the value function via a couple of examples. So what is the typical geometry of this value function? So a classical example is the so-called A-kernel equation of geometric optics. So the differential equation is very simple. It's x dot is equal to u. It means that we have full control on the velocity of the state via u. So u has the same size as x here, and we control the whole velocity. This is a particular case of optimal control called calculus of variations. The state is constrained to belong to a given set, capital X of Rn. The control is constrained to ball, a Euclidean ball, a unit Euclidean ball. And the terminal state must reach the boundary of capital X as fast as possible. So the cost here is this quantity, which is equal to capital T. So among all possible bounded control, given an initial condition in capital X, we want to reach the boundary as fast as possible. So here it's rather easy to observe that the value function does not depend on time, just because if I start the differential equation at time 0 or later on, this will not change the value. There is no explicit time dependence here. We want to be as fast as possible, whatever the starting time is. So without loss of generality, we choose 0 as the starting time. And the value function V star is only a function of the initial condition. So its domain is capital X. So let's take an elementary example, a scalar state X, a scalar control U. So the size of the state and control is 1. And let's take X to be equal to the unit ball minus 1, 1. So what is the value function here? So imagine you start within the minus 1, 1 interval. You control the velocity such that the velocity is between minus 1 and 1, and you want to reach the boundary, namely either the point minus 1 or the point plus 1. So if you are at initial time at the boundary, you do nothing, and the value is 0. And if you are in the middle, x0 equals 0, then you can choose either to go to the left by enforcing u to be -1, the velocity will be -1. You go linearly to the boundary, linearly with respect to time, and you need time equal to 1. Or you can go to the right using u equals +1, and also you go linearly with respect to time. So for all intermediate situations, you have a linear dependence of the value function on the initial condition. And this is the geometry of the value function. So it's 0 at the boundary, it's 1 in the middle, and then it decreases linearly. So you see already on this elementary example that the geometry of V is non-regular. There is a discontinuity of the gradient of V. And remember that the gradient of V plays a key role in deriving the control law. So here it's not differentiable. So when you write the HGB PDE, you must give a meaning to this discontinuity of the gradient here. So that's the HJB PDE, the Kernel JB, sorry. You obtain the Hamiltonian quite easily. And actually, in the suitable notion of weak solution for this PDE is this notion of viscosity solution. You can prove that there is a unique solution in the viscosity sense, and that indeed it is the function of the previous slide, non-differentiable at 0. You can imagine in more dimension that the geometry can be intricate. So for example, if instead of x in R, I have x in R2, and my capital X set is a polygon, here two-dimensional polytope, then the set of non-differentiability points, meaning the set of points for which if you go in one direction or the other direction, you will reach the boundary at the same time. This set, it's called the cut locus, can have a complicated geometry, and this is precisely the set of points where the value function is non-differentiable. So this indicates that this object can be complicated. The value function can be complicated, and since finding the value function amounts to solving the optimal control problem, this could be a challenge. So it's the problem of a wheeled robot problem. Actually, it's the problem of parking a robot where the driving wheels are only at the front of the car, like a normal car, and you try to park it. And so you have control signals. Here you have 2 controls and 3 states. Using a nonlinear change of variables, you can rewrite it as purely polynomial dynamics. It's called the Brocket integrator. And the value function for this is quite intricate. It's for the minimum time problem. It has been studied by many people, including Philip Swear, as I mentioned. And I took these pictures from his PhD thesis manuscript in '93, showing that it's far from being easy to solve the optimal control problem in this situation. So the value function is complicated, it's non-smooth. This is one issue that makes optimal control interesting, but there are other issues. Actually, it's not necessarily even continuous. For example, if I consider the minimum time problem the same as before, but instead of allowing the control to be -1, between -1 and +1, I allow only positive controls, and my target set is, instead of -1 and 1, the boundary of X, only these 2 points, 0 or 1, then the value function, the minimum time required to reach these 2 points, or one of the 2 points, is actually non-continuous function of the initial condition. So it's rather irregular. It's actually just lower semi-continuous function in general. There are even other troubles, other issues with optimal control, is that when I formulated the polynomial optimal control, at the beginning I wrote infimum respect to u. Actually, indeed, in general, this infimum is not attained in the space of functions of time. It is what I mean by there is no optimal control. So here is a simplest non-trivial example we can think of, the so-called Bolza problem of calculus of variations. So it's again a scalar problem. X is scalar with values in -1, 1. U is the velocity of X is also scalar, also in -1, 1. Time ranges from 0 to 1. And I initialize my system at 0, at time 0. And I want to find a control law which make this integral as small as possible. You see in particular that this integral cost is non-convex in the control signal. As a function of u, it is a non-convex function. It's a sum of squares, it's a polynomial sum of squares, which vanishes at plus and minus 1. And in the middle, at 0, it is equal to 1. So it's non-convex degree 4 polynomial. And so intuitively, in order to solve this problem, one can try to minimize, since it is a sum of squares, the two squares here. We'll try to make this guy as small as possible and this guy as small as possible. So let's start with the second one. For this to be as small as possible, u of t should be equal for almost all time t, either to +1 or to -1. This will make this term here identically 0. And this term, for it to be as small as possible, it's simple. X as a function of t must be equal to 0. But u is the speed of x. So if u is equal to plus or -1, x cannot be constant. It cannot stay at 0. So you see that these two terms here, they are conflicting. What we can do, however, is try to approach the best possible value by constructing what we call a minimizing sequence. So this will be a sequence of valid control laws, which will be indexed by an integer that I will denote by r. And when this integer increases, I will get a better and better value for the cost. So on my next slide, you see an example of a minimizing sequence. So in black, I have the trajectory, x, and in gray, the control. It's a function, they are both functions of time. Time here in the horizontal axis. This is the first element of the sequence. I start just by a constant control. The velocity is equal to +1, u equals +1. And then, of course, since x dot is equal to u, x starts from 0 and increases linearly with respect to time until it reaches 1. So let's get back to the problem formulation. This guy is 1 minus 1, 0. This guy is t squared integrated between 0 and 1, so it's non-zero. I can do better if in the middle of the time window, I change abruptly the control from +1 to -1. So -1 means that the slope of my state here will go down and come back to 0. So again, this will be identically 0. And the remaining term here, it's the squared L2 norm of the state. It will be better than this one. So it will be, if you look at the graph, it will be, it's smaller somehow in absolute value. So when you integrate the respect to time, the square of it, you get a smaller value. And we can still do better by alternating plus and -1 for the velocity. And you see that as soon as the state diverges a little bit from 0, then I get it back to 0, like that. And the more I oscillate, the closer I will be to 0. So this is an example of a so-called minimizing sequence, in the sense that I will make this term here, this integral, as close as I want to 0. This term, the remaining term, is always 0. But I will never reach the value 0, actually, because there is no signal u that can take simultaneously the value +1 and -1. So this is a typical example of an optimal control problem which does not have a solution. The infimum is well defined, v star is equal to 0, but there is no solution to the problem. So it's this infimum not attained in the space of measurable functions of time. And as we did already last week, the week before, we'll be enlarging the space of allowable controls. So instead of considering functions of time, we'll consider, with values in u, we'll consider probability measures supported on u, which are functions of time. So instead of ut, I will have omega t. Omega t will be a probability measure on capital U, and it will depend on time. So I use two notations here. It's the same. This is much more probabilistic notation. It's conditioned respect to t. And this is a more compact notation that I will use during the lecture. It's a function of time. So as soon as I fix t, omega is a probability measure on u. If I change t, I get another probability measure. So it's a function of time. So if I now rewrite my controlled ordinary differential equation using this time-dependent probability measure, I just replace here the control u of t, the function of time, with a variable which, with respect to which I integrate. So now it's just a variable of integration, and the integration is respect to omega t on capital U set, support of the measure. So you see that when I do that, I can still retrieve what I had before with a particular choice of omega t being the Dirac measure at ut. The Dirac measure is just a pointwise evaluation. If omega t is a Dirac at ut, I just replace u here by ut, and I get back to my original formulation. However, there is more than Dirac measures. They may be non-atomic measures. And so this controlled ODE is more general. It has more solutions in general than the original one. This is what we call it a relaxed control ODE. So these relaxed controls, they are called also in the analysis literature Young measures. They are designed to capture limit behavior such as oscillation, so minimizing sequences arising in optimal control, as in the previous example. In the sense that it will give sound meaning to limits of this kind, so time integration of a function of the control, this control being indexed by an integer r, and this corresponds to these minimizing sequences, so increasingly fast oscillating functions with bounded values. This gives a meaning to this when r tends to infinity, so the speed of oscillations, if you want, via this integral for all test functions. So as a first exercise for you to manipulate this object, I'm asking what is this limit? What is this relaxed control here when the sequence here, you are, as a function of t, are sine functions with increasing frequency here. So r is an integer, and you see this takes bounded value between -1 and 1, but the oscillation becomes faster and faster. We can still give a meaning to the limit via specific choice of omega t here. And so the exercise is asking, what is the choice? So let's see for the classical Boltzmann problem, what is the value of omega? So as I said, instead of plugging a classical control signal here in the optimal control problem, I plug a relaxed control. So as soon as I see control signal, I replace by an integration variable, and then I integrate respect to u this function, respect to omega on u, this function. I do that for the ordinary differential equation as well. And now, instead of u, I have a blue guy here, which is my new unknown. It's a probability measure with values in the control set. We can prove, and that's the second exercise of today, that actually there is no gap between these two problems, between the original Boltzmann problem and the relaxed one. So we saw already that the original value is v star equals 0. And so the exercise is about showing that the relaxed value is also equal to 0, and that the optimal solution here, omega, denoted omega star, is actually equal to 1/2 the Dirac at -1 plus 1/2 the Dirac at +1. So somehow optimal control law is a superposition of two possible control laws, the one at -1 and the one at +1. Can prove that this infimum is attained. Actually, you have to prove that it is attained, and hence that this problem has a solution contrary to this one. So let's relax. That's the leitmotif of this series of lectures. Instead of considering a classical POC problem with classical functions u of time, we consider a relaxed POC problem with infimum replaced by a minimum, and the argument here, instead of a function, becomes a relaxed control, a probability measure on the control set depending on time. So it can be shown that under reasonable assumptions of convexity, there is no relaxation gap, namely when I enlarge the set of control from classical control to relaxed control, I do not change the value. Another way to understand that is that every relaxed control will be a limit of a minimizing sequence of classical control. So that's the relaxation procedure as far as the control is concerned. But here you see that there is still nonlinearity. If I want to carry on the LAAS program, the step 1 is linear reformulation. I still have to deal with a nonlinear function of the state here. So now I'm linear in the control through the relaxed control omega, but I'm still nonlinear in the state. And so my next developments will be about linear reformulation of the state as well. And as you may have already guessed, there will be a probability measure not only on the control set, but also on the state set. But before we go into that, let me take a few questions in the chat. So, Okay. Questions? No question about relaxations in control, relaxed control, limits, minimizing sequences, existence of a minimizer. Okay, so let me get back to the slides then. I hope the screen sharing works. So as I said, we relaxed, but we are not relaxed enough. We are not fully linear. The problem is still non-linear in the state trajectory. And this is why we introduce now a measure with respect to x as well. So if you attended the lecture of last week, this is a continuous time counterpart of the discrete time occupation measure that we saw already. Its definition is the following. So it's a measure of time state control, which is defined for each given initial state. So it's a condition with respect to x0. And the control part, actually, this measure here is given. So this is also given, time, uniform, the control, so it's conditioned on time. And what remains here is the state, which is, of course, a function of time, a function of control, and also a function of the initial condition. This measure, I take it concentrated on the trajectory corresponding to this initial state and relaxed control. And this is my definition of occupation measure. So this occupation measure is useful when I want to integrate an observable test function along trajectories. A function of the state, maybe some energy I would like to evaluate, some performance criterion that I would like to evaluate. And from the definition of occupation measure, this time integration along trajectory is actually the same as integration of the occupation measure with respect to v. So this is my notation, the duality notation of 2 weeks ago. So as soon as I have an integration with respect to time, I replace it by a space integration on the support of mu. Now, if I do that systematically to evaluate the difference of an observable of time and state between time t0 and time capital T, so I use the fundamental theorem of calculus to notice that this difference is just the integral of the total derivative, but this total derivative is also the time derivative, the speed integrated uniformly with respect to time, dv over dt times dt, and dv over dt is actually equal to the sum of the partial derivatives. So v is a function of time and state. So dv over dt plus dv over dx. But since x is a function of time, this is dv over dx times dx over dt, which is f. This is a prescribed velocity in my ordinary differential equation. So that this integral here can be written formally like that, where L is a linear operator from the space of continuously differentiable functions to the space of continuous functions. So my difference of observables at initial and terminal time is the integration respect to time of this LV function along trajectories. And since integration respect to time along the trajectory is by definition space integration respect to the occupation measure, I can just rewrite this with measures. Rewrite this by using Dirac measures concentrated on time and initial condition and terminal time and terminal condition. And this is a space integration I had before. This, you can see that in the sense of distribution, I can rewrite it without the test functions as I did last week. Just have to introduce the joint operator, L joint. And here, I'm sorry, there is a typo. This is L a joint of mu, not of V. It acts on measures. So LV mu is equal to L adjoint mu V. It's the adjoint. And the joint operator is defined like that. It's a first order differential operator acting on measures. So if you're not familiar with these notations, just have to keep in mind that what I mean by this Duville equation is just this equation for all possible C1 functions of time and space, C1 functions V, for all test functions. So what I've done so far is to reformulate a nonlinear problem, a Cauchy problem, the initial condition is prescribed, into a linear problem at the price of introducing these occupation measures. So you see that the right-hand side of the Duville equation here is given. It is the initial measure that I denoted mu0. It's concentrated on initial condition. And otherwise, what remains here is mu, the occupation measure, and mu capital T, the terminal measure. So basically, it's a method of characteristics. If you're familiar with analysis, the characteristics of this first order transport PDE are precisely these ODEs. And this is a way to prove that there is, given right-hand side here, a unique solution to the Duville equation, provided there is a unique solution to the Cauchy problem. So if f is polynomial, it is Lipschitz, there is a unique solution. And it's state conditional. The state conditional risk of mu is concentrated on the solution of the Cauchy problem. So the x component of the measure here, which is disintegrated, actually is a Dirac measure. This is true for classical control, but this is also true for a relaxed control, in which case the conditional measuring the control here is not concentrated on the graph of a function, it's just this relaxed control that we saw before, omega t. So to summarize, I replaced a nonlinear Cauchy problem with a linear Duville problem. And this is actually all I need to carry on the first step of the LAAS program, linear reformulation. Since the integrand in my original POC are time integration along trajectories, this corresponds to space integration of occupation measures, here of the whole occupation measure, and here are the terminal occupation measure. And instead of my nonlinear ODE, here I have the linear Duville equation. So I replaced a nonlinear, non-convex problem on functions with a linear problem on measures. And under the no relaxation gap assumption that I mentioned before, we can prove that there is no gap between this original problem and the linear problem. So the values of both problems are the same. As we did already many times, we can use convex duality to derive a dual to this primal measure linear program. it looks like that. It is actually an exercise for you to derive the dual using the Lagrangian and Lagrange dual function, the same strategy already followed twice if you followed the previous courses. And you see there are two constraints corresponding to the two measures here in the primal. And there are positivity constraints on continuous functions. We can prove as well, that's the topic of the exercise, that there is no duality gap between these two infinite dimensional problems, the primal on measures, the dual on continuous functions. And since P star was equal to V star, this also solves the original POC. So we are done with the first step, the linear reformulation. And before I allow time for questions posted on the chat, I will go through the second step very quickly, like last week. The construction of the hierarchy of convex relaxations. Actually, there is nothing new here. All the data are polynomial, L, L, T, F, X and U, XT are basic semi-algebraic, bounded. So everything is under control. And so we can really plug and play the moments of hierarchy, this mathematical technology, just by replacing this cone here, the cone of non-negative continuous functions, with these truncated quadratic modules, this sum of squares. And in a dual, we replace these with explicit moment and localizing matrices, these linear matrix inequalities on the pseudo moments of the occupation measures. Doing so, we get sequences of primal values, P star R, and sequences of dual values, D star R, that are actually equal to each other. There is no duality gap in the relaxation. And we get on the primal approximations of moments of the occupation measures, what we call pseudo moments. And in the dual, we get a sequence of polynomials, these quadratic modules, V sub R of increasing degree R. The last step, as you may have anticipated, is about proving convergence properties of these relaxations. But before, some time for question. As usual, on the POEMA website, you can find the slides. I will update them after fixing the usual typos. And also the notes, which are attached to the lecture. So I will give their pointers to technical literature. Okay, so Monique Laurent is asking, what are the convexity assumptions for having no duality gap? Actually, there is, for the linear programs, there is no, for the infinite dimensional linear programs, there is no convexity assumption. As soon as we have compact supports, we already talked about relaxing the compactness assumption. This is also possible. Usually we have bounded trajectories, bounded controls, and As soon as we have that, we have polynomial vector field. So we have given a control unique solution. There is no duality gap in the linear programming formulation. What can occur is that there is a relaxation gap between the problem with classical controls and the problem with relaxed control. But this occurs only in the case of a very intricate and stringent state constraints. So in my opinion, these are problems which are mostly of mathematical interest and that do not occur in practice. So the convexity assumptions that are made to avoid the relaxation gap are very reasonable. So if you want to know more, I give references in the lectures, in the lecture notes. This is a little bit technical. So are the inf equal mean reached here? Why? Is asking Bernard Morin. So usually when you formulate infinite dimensional optimization problem, in particular linear optimization problem, if you are not careful enough, the minimum is not attained. And a way to retrieve attainment, in a way to ensure that the infimum is actually a minimum, is to formulate the problem in a dual, in the topological dual of a functional space. So example of a topological dual would be, for example, L infinity, uniformly bounded functions, or spaces of measures. So as you know, measures, non-negative Borel regular measures, they are compact sets, they are topologically dual to non-negative continuous functions. So when formulated in dual spaces, the optimization problems are much more well behaved. And this is the case for the problem on measures. So for the polynomial optimal control problem, we can prove that problem on measures as a solution. The problem on C1 functions, as I defined it, will not have a solution actually in the C1 function class in general. So in that sense, measures are much better behaved than functions. Ramtin Davoudi is asking whether it is possible to generalize the framework for POC to fractional OCP, which includes fractional differential equations. That's an interesting question. Never thought about that. I don't know. One has to do the analysis carefully, but indeed, fractional derivatives, as soon as you can write them as semi-algebraic constraints, there is a potential of having the things carried out. I don't know if somebody ever attempted that. Interesting question. Thank you. Are there other questions on the lecture of today? So I'm, let's say, in the 2/3 of the lecture. The rest will be about convergence statements and then examples. So if you have questions that arise to you in the meantime, just post them onto the chat and I will go through them after I'm done with the remaining of the lecture of today. So let me share the screen again. Get back to business. So I've got my linear primal formulation on measure and dual formulation on continuous functions for my POC. I replace here my favorite cones by my even more favorite cones, the truncated quadratic module based on sum of squares and its dual. And hence, I'm wondering whether these sequences here obtained for increasing relaxation order converge to the right values. and also what I can learn from the polynomials here that I obtain in a dual when solving the sum of squares problem. This is the third step of the strategy. So first, it's rather easy. It's an exercise for you to prove that for every dual admissible function v, so function v satisfying these two inequalities, where this just means that this must be positive on the support here. Then every admissible function is a lower bound on the value function. So it's a lower bound which is valid everywhere. And since we are maximizing the value of v pointwise at the initial data, there will be an admissible sequence that will touch the graph of the value function at that point from below. So if you're familiar with viscosity solution, this will remind you of something. So it means that will get a sequence in the dual that will approximate as closely as desired the value function at a given point. And actually we can say more. Not only the difference between the value function and the approximation of it, say using polynomials, goes to 0 when R, the relaxation order, tends to infinity, but the gap between the actual value and the approximation gets smaller when I integrate the trajectory with respect to time. So for any optimal trajectory, the difference of the value function, its approximation, gets smaller than the initial difference. The gap between the value function and its lower bound decreases along optimal trajectories. So this is true for any optimal trajectory, and so if there are several optimal trajectories, this is also true for all of them simultaneously. So this is in particular true for the polynomials obtained with the hierarchy. Sorry, it's stuck. Yes. And however, you see that we just insist on the value of the value function at one point, given time t0, given initial condition x0. This meant that in the Liouville equation, we had the right-hand side, which was concentrated at t0, x0. But we can proceed exactly the same if instead of having concentration at a given point, we have a given point x0, we have a general probability measure supported in the state set, xi0. So that instead of a single initial condition, I can optimize over a whole set of initial conditions. So in terms of occupation measures, this is something we saw already last week. This will be the operation of averaging with respect to distribution of initial conditions. So the average occupation measure will be defined like that. The value function also becomes average, and so is the dual and the primal value in the LP formulation. So when I proceed like that, roughly speaking, I will get through this slide, which is a little bit technical fast. What I have is that actually instead of having good approximation of the value function only at a given point, we have it xi0 everywhere, almost everywhere, in the following sense. And then when time evolves from time 0 to bigger times until capital T, this quantity here decreases, where here I have Xi of t. Xi of t will be the image measure of the initial distribution through the flow map of the controller. So this is the convergence result that we had. And again, this applies for every maximizing dual sequence, in particular the ones that arise from the moment source relaxations. So two examples to conclude. The first one is the so-called turnpike control. It's a classical problem optimal control. Well, the optimal strategy is to control at the beginning, then to do nothing during some time, and then to control at the end, just like when you're driving on a highway. And it is formulated like that. It's nonlinear. And here's an example of an optimal trajectory, x of t, starting at initial time and initial condition 0, 0. This is a scalar problem. So this problem can be solved analytically. It's a good example in the sense that we have the value function. I will not write it down, but it can be computed. And so we can plot the differences between the analytic value function and the approximations using polynomials of increasing degrees, VR, along the optimal trajectory of the previous slide. And you see that, of course, the gap between the value function and its approximation decreases when the degree increases. So the bigger the degree, the better the approximation. But also, already for small degree of VR, the quality of the approximation increases when time increases. So along trajectories, the approximation becomes better and better. This was this is the illustration of the theorem. The second example is the linear quadratic regulator set control. It's a very classical example that can be also solved analytically using algebraic Riccati equations. It's a linear dynamics and quadratic convex cause, so everything is known about this problem. And here what we plotted is the contour line in logarithmic scale of the difference between the value function, which can be found analytically, and the approximation of degree 6. You see that, so the smaller the exponent, the better the approximation. Here we have 3 digits of quality of approximation. And you see here also that this gray region is actually the set of trajectories which is obtained not by initializing the ODE at a single point, but at the whole ensemble of initial conditions, the support of this C0 measure. Here, uniform between -1 and 1. And you see here the support of the measure shrinking, just because this ordinary differential equation is stable and everything will eventually converge to 0. You see that these level sets of trajectories match the level sets of the difference of the value function as predicted by the theory. So this is it, and this will be the last slide that you saw already many times if you followed the 3 lectures. The main ideas, the main steps of the moment sum of squares or LAAS hierarchy. So today illustrated on polynomial optimal control, nonlinear, non-convex problem, reformulated at the price of working in space of measures as a linear program. This linear program, which is infinite dimension, is then truncated and approximately solved by a family of convex relaxations using sum of squares. And thanks to properties of these quadratic modules and positive channel ZC of real algebraic geometry, we can ensure convergence of the hierarchy. And also conic duality has been used often to help us to this purpose. I'd like to thank you for your attention for this lecture and the previous ones. And I'm ready to take your questions on the on the chat. We can also get back to the exercises of the second lecture if you're interested. Now, as to the 4 exercises of today, I will post in a few days written solution on the website for you to check. Okay. Other questions? And Giovanni Fantuzzi is wondering whether it is possible to extract an approximate optimal control law from the solution of the moment source problems. If so, could you please give an idea of the strategy? Thank you, Giovanni, for this very relevant question. So I indeed will put references in the lecture notes. When you know that the occupation measure is concentrated on the graph of a function, indeed we have techniques to approximately retrieve the graph. So the more you have moments, the better you can construct an approximation of the graph, and we have convergence guarantees in L1. And this is actually a very nice question because this is an introduction to the next series of lectures of Edouard Powell's on the Christoffel-Darboux kernel approximation. So we use this Christoffel-Darboux kernel to approximate as closely as desired in the L1 norm the graph of the function from the moments of its Young measure. So I'll give a pointer to the reference in the lecture notes, but if you're interested in these techniques, I welcome you to attend the lectures by Edouard. They are starting next week. Ramtin Davoudi is asking, could you please explain more about what you mean by transporting the Lebesgue measure? Oh, yeah. Yes, I went a little bit fast through that. If you formulate the Cauchy problem as a Liouville equation, as I shown, the right-hand side of the Liouville equation was concentrated at time t0 and state x0. Now, if instead of the Dirac measure at x0, you have any probability measure, instead of just solving the Cauchy problem, the ODE for a single atom, x0, you solve it for all possible atoms in the support of the measure. And somehow the solution of the Liouville equation will be just a superposition of all solutions of all these Dirac measures supported on the solutions. And so this is the intuition behind it. In order to make this rigorous, you use the notion of image or push forward measure that we saw last week already. And here the relevant notion for defining the push forward measure is the notion of flow of ODE. So the flow map is the time-dependent map that associates to a given initial condition, x0, the solution of the ODE at time t. So the image measure of the flow map, the image measure of the initial measure, C0, through the flow map is this measure CT that you shown in my that I shown in my slide, and that is solving the Liouville equation when the right-hand side is not concentrated. So I hope this explains a little bit. If not, I welcome you to go to the lecture notes and to have a look at the references.
Thank you, Didier. So all the material of your presentation will be available on, or is available already on the website of POEMA.
Yes, it will be updated since I found already typos, and I will put a few more references to address the questions of the chat. Indeed.
Very good. So thank you very much. And so next week we will have the first lecture by Edouard Pauwels on Christoffel Darboux kernels. Thank you.
Thank you all for attending. Thank you, Bernard and Lynn, for organizing. Also, thanks to Marcos for his help. And see you soon.